nanohub.org.
We covered last week the basics of the point mass oscillator model for an AFM. We made the difference and the distinction between free oscillations, which in the vibrations terminology refers to when you just take the cantilever and ping it and let it just die out. That's what free refers to. And then we talked about forced vibrations, when you actually drive it with some excitation. What's the response of these two things? There's a distinction to be made between the two. And we talked about what happens when you take this oscillator model and then bring it close to a sample surface so that the FTS, the interaction forces, start affecting the dynamics of the oscillator. And we said that right away off the bat, the equations of motion that govern it would be nonlinear, and they would not be so easy to understand. And so we said we would try linearizing the equations, and the linearized analysis showed some interesting trends, which suggested that the change in amplitude and phase you might get as you approach the sample have to do with the force gradients, the gradients of the tip sample interaction force that you encounter. So that's how we started, but we also were very cautious and said that the linearized analysis holds only when the oscillation amplitudes are really, really, really very small, which in principle is, under most circumstances, is not met in most experiments, okay? So let us now take a step back and try to understand what we are trying to do today. One of the first things that happens when you do tapping mode AFM, right, is you take a cantilever, as shown here on the top, far from a sample, and you do what's called a tuning curve, which is you just sweep the drive frequency across resonance, locate the resonance frequency, and you get an initial amplitude A in it and initial phase phi in it. Okay. Now, in the literature, you will often see this referred to as free amplitude and free phase, because in the AFM literature, free they refer to as when it's not interacting with a sample. But since we're trying to do this rather holistically within, vibrations theory, in vibrations theory, free refers to a different thing. It refers to when you just ping it and let it die out naturally. That's what free vibrations refers to. So we won't mix it, and we'll just call this the initial amplitude A in it, initial phase phi in it. And you approach a sample, as you do, what happens is the amplitude and phase would change to a value A and phi. Okay? So the approach curve refers to the process shown in blue, where once you have chosen once you have done a tuning curve, chosen the resonance frequency, gotten an initial amplitude, initial phase, you approach a sample. What a dynamic approach curve refers to is tracking how A changes from A init to A, how phi changes from phi init to phi as you change Z along the blue arrow, okay? So this is what happens in tapping mode, because in tapping mode, you always keep the drive frequency fixed as you approach a sample. When you do frequency modulation, you don't do that. You actually change the drive frequency as you approach a sample. But in tapping mode or in amplitude modulation, drive frequency is fixed. Okay, so once you sort of bring it close to the sample, the amplitude and phase are going to change. Why do they change? Because of tip-sample interaction forces, right? We've already seen a very simple example. When you linearize equations of motion, you will change the phase and amplitude because the frequency shifts, right? So that's why the amplitude and phase would change. And as you scan a sample, what the controller tries to do is tries to move the base of the cantilever, whose locus is shown in red. It tries to move the base of the cantilever up and down in order to keep the amplitude, the observed amplitude, constant, right? So it uses the amplitude signal as a feedback, as a controlled feedback, scans over the sample. So in principle, as you scan over the sample, what's going to happen is when you hit like an edge, as shown here, the controller is going to have some transients, right? It's trying to maintain a constant amplitude, but what happens is it feels this object and it sees that the amplitude is starting to change. You need to give the controller some time to compensate for the changed amplitude and move the base of the cantilever up. So there'll be some transients as shown on the left-hand side of this, edge feature, and then it'll stabilize along the flat red line. And then when you go off the feature, again, there's going to be a transient. We call that process of parachuting off. Okay, so it parachutes because it's tapping, and suddenly there's no sample underneath it. So the amplitude changes suddenly, and the controller needs to sort of respond to that and bring down the cantilever, so the amplitude reduces again to the set point amplitude A. So A is referred to as the set point amplitude usually in this curve, okay? So this is the whole picture of you do tuning far from a sample, approach a sample, and then you scan, okay? So what we'll study today is we're first going to do tuning, then we're going to talk about approach curves. We've already done tuning curves effectively when I showed you what the frequency response is in magnetic and acoustic excitation. But we're going to study what happens when you do tuning close to a surface, because understanding that really helps you understand what the dynamic approach curves are really telling you in experiments, okay? So that's the connection. So a quick review from last time with the point mass model. We saw that if you have very small oscillation amplitudes, you can do a Taylor series expansion of the interaction force FTS about the equilibrium position of the cantilever, which is shown on this graph by a green dot. So that's the green dot represents the gap, the D star value at which the cantilever has equilibrated, right, from the sample. And what one is basically doing is one is writing the tip sample interaction force as a Taylor series expansion. The first term of the expansion is basically the slope of the interaction force at that point, right? That's the first, and the slope of the interaction force is partial phi partial d. That quantity, if you think about it, is a spring, isn't it? So whenever there's a linear gradient, it's like a spring, except what happens is, if you look at the equations of motion, that gradient appears with a negative sign on the left-hand side of the equation, right? So what that means is, whenever you have a partial f, partial d is positive, whenever the slope is going up, you actually get a negative, so there's a negative sign there, so you get basically a decrease in frequency, okay? So in other words, whenever you have an attractive gradient, so let's step back a little bit. When you look at this f versus d curve that we have here, right? We have what are called attractive gradients, and we have what are called repulsive gradients, okay? An attractive gradient, according to this scheme, would be whenever the slope is positive. Partial f, partial d is positive, basically everywhere to the right of that minimum force point. Near to the right of that minimum force point, partial f, partial d is positive. Everyone with me on that? Yeah? Okay? So whenever you're in that, whenever your green dot is to the right of that minimum, partial f, partial d is greater than 0, and we call that an attractive force gradient. Not an attractive force, but attractive force gradient. And that feeds into the linearized equation, as I showed you right-hand side, with a negative sign, and that's going to reduce the natural frequency of the oscillator, okay? When you bring the cantilever, the blue dot, very, very close to the surface, so that the green dot is now to the left of the minimum point in this force, partial f, partial d becomes negative, correct? So to the left of the minimum, the slope is negative. So if you come very close, where you're to the left, where you come so close where you're left of the minimum in this interaction force, partial f, partial d becomes negative. And then going back to the equation of motion, you have another negative here. So two negatives make a positive, and that causes an increase in the resonance frequency. So the bottom line of this linearized analysis that we discussed last time was that the interaction force can be considered if your oscillation amplitudes are really, really small. The interaction forces can be just thought of as a spring, because the only effect it has on the cantilever is in sort of shifting the frequency. So it's a spring, effectively. That's what is shown here. And when you're to the right of the minimum point, the spring is something like what's called an attractive spring. It's a spring that sort of sucking the cantilever in. And what it does is, it's an attractive spring, we call it. Most springs we're used to are repulsive, right? In that they restore. But there are some, you can think of negative springs that as you push, they pull further down, you know? That's what it is. And when you come sufficiently close, the linearization of the equations of motion suggests that you have a repulsive spring, a repulsive force gradient, okay? So this linearized analysis would suggest that if you did a tuning curve, you just sweep the frequency across resonance, then you would get what is shown here at the bottom right, right? The solid black curve would be a nice resonance curve, but when you start interacting with the sample, that resonance curve would shift to the dotted, to lower frequencies, due to attractive gradients, okay? On the other hand, if you come much closer to the surface and you are in the repulsive gradient regime, then the tuning curve would change from the solid black line to the dashed black line. The resonance would shift up, okay? Right? So what this suggests is, what the linearized theory would suggest is that if you're far from a sample and you tune, you just get a nice curve like we have shown before. We wrote the equations of motion for it. As you come closer, that curve just shifts to the left first, or sorry, from your point of view to the left, to lower frequencies. But as you come closer, this curve shifts back and moves to the right, because you're now in the repulsive gradients. Now remember, in this entire process, our drive frequency is fixed. So as you approach the sample, what you expect is first the resonance frequency peak moves to the left, so you should get a drop in amplitude. But at some point, as you come close, the resonance frequency starts increasing. There's going to be increase in amplitude again, and then a decrease, right? So if you think about what this suggests regarding what's going to happen to the oscillation amplitude as you approach a sample, you get a very weird answer. You get an answer where the amplitude should decrease and then increase again. In reality, all that doesn't happen. And the reason is that under most circumstances, this linearized analysis is not valid in AFM, okay? Why? You have to ask the question, what we're trying to do, if you think about it, is we're replacing the interaction force shown in the red curve at that point, which is shown as green, effectively we're approximating it by that straight dashed line, right? That's what the linearized approximation is. We're saying we can approximate that curve by a straight line locally. Well, obviously that approximation is going to be valid only for amplitude that is small enough, right? The question is, how small should that amplitude be? Well, the answer to that question is, it's a Taylor series expansion. So the first term in the Taylor series expansion is partial f, partial d. The second term is the second derivative, i.e. the curvature of this curve. So you can show that in order for the straight line to very well represent the interaction forces as it oscillates, you need the oscillation amplitude to be much smaller than the slope of the interaction force at that point. So the slope of the curve divided by the curvature of the curve at that point. Okay? In practice, this amounts to oscillation amplitudes of about, it depends, maybe an angstrom or less, which is basically, most of us are not able to do this. Okay? So, which is why it gives this simple linearized analysis gives a very nice idea, but what you predict from it is not what you see in experiments. Here's an example of how it actually behaves. So remember, the linearized analysis just simply says that as you approach a sample and you do tuning curves, as you approach a sample, the resonance frequency, the response remains like this, but it just shifts left and right. In reality, this is what happens. This is an example where you're oscillating a cantilever on a graphite surface, and you're sweeping the frequency. It's a large amplitude motion, and this is on graphite, and the amplitude behaves like this when you're near a sample. Whereas when you're far from a sample, it behaves like shown by the solid black curve, which is the sort of the peak in the background. You see that? There's a peak in the background. That's the curve, the tuning curve you get as you sweep back and forth when you're far from a sample. When you're closer to the sample, about 100 nanometers close to the sample, or actually, 80 nanometers. By the way, this amplitude is peak-to-peak amplitude, so the real amplitude is half, okay? So when you're about 80 nanometers from the sample and you sweep the resonance frequency, the drive frequency across resonance, you get this behavior, right? You get this interesting, two things you observe is there's like a truncation of this peak, original peak gets sort of truncated in some way. And the second thing you notice is as you sweep up, you get a very different response as when you sweep down. And this is where the nonlinear nature of this really comes in. And you actually see it very nicely in the phase. When you look at the phase, what happens is at the same points where the amplitudes jump up and down when you sweep up and down, the phase also jumps up and down. This is what happens. So this is very interesting, and it has to do with the fact that as soon as that requirement, of the amplitude being less than an angstrom, as soon as that is not valid anymore, then the system becomes much more complicated, and you have the possibility of multiple oscillation states. And the fact that you have you sweep up and increase and decrease the frequency, you get different solutions, suggests that multiple solutions are lurking out there, and you're jumping from one solution to the other, right? So we'll now try to discuss what are these multiple solutions that happen when you try to do tapping mode near a sample. So think of this as suggesting very fundamentally that in reality our oscillation amplitudes are larger than the 1 angstrom, and therefore we are going to encounter effects like this. Okay, so the question is, what does it do, or what does it really mean? Okay. Okay, so this is a summary of what I'm trying to present here today. Okay, on the left column is the linear approximation. The middle column is when the amplitude of oscillation is slightly larger, and on the rightmost column is when it's the largest of the three cases. Okay, so what we're looking at is simply, let's say the cantilever is at some fixed distance from a sample, but close enough where there's an interaction now, and you sweep the frequency up and down, drive frequency up and down. Look at the tuning curve, right? So I'm just looking at what is happening to the tuning curve as you increase the oscillation amplitude. So if your oscillation amplitude is an angstrom, we know what you see is there, right? i.e., if your oscillation amplitude, as shown by the green bar, if it's small enough, then you can see that it's reasonable to represent the interaction force by just a gradient, by a straight line, right? So your approximation will be right, linear approximation, and your response will be as shown here. You get a resonance peak exactly at omega 0, right? And your phase goes, from 0 to minus 180 degrees, and at resonance you're at minus 90. So everyone knows this, right, from basic oscillator theory. Now, on the other hand, if your oscillation amplitude is larger, as shown in the second column, so that you're now traversing a larger part of that interaction potential, you can see that that green curve that it's going to be absolutely incorrect to approximate the interaction forces by a simple gradient, by a straight line anymore, right? They've got a lot of curvature going in now, right? So you cannot approximate it by a straight line. By the way, in air, on normal surfaces like mica and such, this F versus D curve pretty much lasts for 2 or 3 or 4 nanometers. That's it. So we're talking already about oscillation. This would happen even if your oscillation amplitudes were 1 or 2 nanometers. It would happen, okay? Which is, again, much smaller than most people ever deal with in AFM, okay? So my point is, it's always there, especially when you do this in air. You have to be careful about this. So it turns out that whenever the oscillation amplitude is slightly larger, so that you're kind of going in and coming out, and now with this oscillation amplitude, if you were to sweep the drive frequency across resonance, the resonance curve becomes as shown here in the middle, okay? It's hard for me to explain fully why this happens. You will explore this in the next class using simulations. And when we continue this, I think next week or next week actually, we will try to develop an analytical understanding of why this happens. But without an analytical understanding right now, simulations are just going to show you this, right? So let's first understand what happens and provide some physical context to it. And then more analytical, integrals and expressions that prove that this is what happened will come later, okay? So this is a picture of what happens. What happens is the resonance curve. So I've shown in the second column that the amplitude is larger. You see, the height of this peak is larger compared to the first column. So slightly larger amplitude. The linear approximation is no longer valid. And the tip is still in the attractive regime. You see that? The tip remains in the attractive regime. What the resonance peak does is it tips a little to the left. So it becomes asymmetric. It does this, okay? And if you think about the dashed line suggests that there is sort of a backbone to this peak that curves a little bit. It goes up and curves. Whereas in the linearized response, that backbone is simply a straight line. This curve pretty much is sort of symmetric about that one line. Whereas in this case, you've got a backbone that curves like a hockey stick, right? And accordingly, if you do simulations, and you'll do this on Thursday, when you do sweeps, you find that the phase distorts as shown here in a very interesting manner. And the 90-degree point is actually at this little cusp here that happens. So just simulations are going to show this to you, okay? And experiments like I showed you, when you do tuning near a surface, you actually pick this up, right? As you go to slightly larger amplitude, so at the same distance now, let's say you're shaking more and then tune the tuning curve, right? So that your oscillation amplitude is large enough that your tip goes through the minimum in the interaction force, but goes into the repulsive regime and back in each oscillation cycle. When you're in that situation and now you sweep the drive frequency across resonance, you get an amplitude versus frequency curve that looks like this. Really cool. Resonance curve is no longer linear. It just gets distorted completely like this. And the phase, again, gets really distorted in an interesting way, but what still remains true is that the 90-degree point, phase equal to 90-degree point, corresponds to the apex of the resonance always. So the resonance curve can move this way, it can bend both ways, but the tip is where the phase is 90 degrees. Okay? This is what simulations will show you and experiments will show you. Okay? Any questions on this? But now we're going to see why this happens, what this happens. But I hope you appreciate that this linearized analysis, obviously, the simple analysis is only going to be valid when the oscillation amplitude approximates, well, the interaction force. And as soon as you go to the second row, you're obviously not approximating it well, and so you get this. Third row, you're completely missing. I mean, if you represent the interaction force by a straight line, you're completely wrong, because the interaction force the tip is encountering is this very complicated green curve, right? Okay, any questions on this? Yes?
Fair question to ask if anybody in the class has actually seen this behavior. When they do the tuning curve. Has anybody actually seen this?
Well, the thing is, so it's a good question, and you will see. So most tuning curves are done when you disengage from a surface. When you disengage from a surface, you're 2 microns away from a surface typically. So there's no interaction forces. So that's just to look at the response when you're in the initial faraway state. To see this, you have to engage the surface and then jog it by 100 nanometers, or keep it there and sweep the frequency. This is not something that, most AFMs, I mean, you have to send an email to the manufacturer, tell them, I want to do this, and they'll say, well, disable this or enable that, and then you can do it. It's a special function. So we're not suggesting you do this, but the reason we're showing you this is because understanding this is actually key to understanding what happens to the amplitude and phase when you approach a sample, which is what everybody does, which is the dynamic approach curve. You don't understand dynamic approach curve well enough if you don't understand this. That's the connection. So you wouldn't, experimentally do tuning curves so close to the surface, but this really helps understand what's going on. Okay? In particular, I want to highlight 2 important things. I do want to highlight the fact that what can end up happening is, so for example, you can actually have situations, number one, where at a given frequency, there can be two oscillation amplitudes. You see this? So I can take, depending on the drive frequency, I can take a drive frequency somewhere here, but I look up and there are more than one amplitudes possible for a given drive frequency. So that certainly suggests that you have the possibility of multiple oscillation states going on. And so as soon as you have multiple oscillation states going on, you have to start worrying on AFM about, oh my goodness, if my oscillation state changes, my image may change. And so certainly the first thing that should come to mind is, if oscillation states are different, why are they different? How are they different? And do they switch during an image? If they start switching during an image, then you have a problem, right? So it turns out that what happens is, if you look at the column on the far right, if you're on the very top plateau, right, you are in what's called a net repulsive regime of oscillation. In other words, the tip, not only does it come through the minimum of the interaction force, but it goes up all the way until the net force it experiences is actually positive. All right? That's what happens in the very top here. At any other place where you might be, you're actually at a situation where, as the tip oscillates, the net interaction force encountered is actually attractive. Okay? So again, the reasons for this will only become clear when you do the analytical part. So we had to do some integrals and some approximations to really see how this happens. Okay? So there's a separate class on the analytical approaches to this. Okay? So the key part I'm trying to say is that the different solutions you might get here reflect two kinds of oscillation states. One oscillation state where you're oscillating at large enough amplitude that you go through the minimum of the interaction force and actually go deep enough into the repulsive state where then you have a net repulsive interaction. And the second state of oscillation where you oscillate so that you have a net attractive oscillation state. So these are the two main oscillation states that are represented in these multi-valued curves. Okay? So usually one branch of it is what we call net repulsive, another branch is net attractive. Okay? So let us see how this plays a role. Okay, so it's actually important to try and understand why this happens. So here I'm going to give you a physical reason. Maybe it helps you understand why these curves, if you don't have a background in nonlinear oscillations, why do these curves bend due to nonlinear interaction forces, okay? Would that be a fair thing to look into, just to provide some background as to why you should expect them to bend either way? Okay. One way to understand this is looking at it from potential energy of an oscillator, okay? So the cantilever itself is like a spring, right? It's the point mass model, right? So its potential energy is going to be 1/2 kx squared. It's a quadratic potential, right? So what is shown here at the bottom is the potential energy of the cantilever at some distance z from a sample. So you're at a distance z, and as you bend the cantilever from that equilibrium position, its potential energy increases quadratically from the equilibrium position, right? So you have that. However, you also have another source of potential energy, which is the tip sample interaction forces, because you have conservative interaction forces. So conservative interaction forces means there's a potential energy associated with it. That potential energy is shown on the top. Okay, so the total potential energy of the system is going to be the sum of those two, right? The tip sample interaction potential energy and the cantilever potential energy. So what you have is the net potential energy landscape is due to this quadratic in the interaction force and this nonlinear potential energy due to tip sample interaction. You're adding the two together. And the addition gives you the total potential energy, okay? So under most circumstances, when you add the two together, the potential energy looks a bit like what is shown on the top right, okay? On the top right, you see that the cantilever is located at a distance about 5 nanometers, which is where there's a minimum, right, of this potential energy. And locally, potential energy goes quadratically. But as the oscillations on the left side approach the sample is on the left side, you get an additional term due to the potential energy of the van der Waals and the repulsive interactions. So that on the left side of this potential landscape, you're distorting the quadratic potential well by the potential well of the tip sample interactions. Do you guys see that? This is the top right curve. It's not a pure quadratic anymore. It's basically, I'm superposing, I'm adding these two. Okay? Now, you can imagine that depending, the resulting potential energy landscape depends on the original Z, right? So if the quadratic potential well is located far off to the right and you superpose it, that's what you get on the top right. On the other hand, if the quadratic potential well is brought closer, if the center of it is brought closer, as shown here, you could get a picture like this, right? So you can see that depending on how far the Z is, the overall potential energy picture depends, okay? So under most circumstances, when you do dynamic AFM, you're in a situation shown on the top right. You're far enough away where the effect of the interaction potential well is to simply distort, the potential energy function from a pure quadratic. When you come very close, you get two minima, which corresponds to the fact that you can have the tip that can either be stuck into the sample or away from it. So each minimum of a potential energy is an equilibrium position, right? But we won't concern ourselves with the bottom right figure because that's not what typically happens. In a dynamic AFM, you're far enough from a sample where you're talking of a fundamental quadratic energy landscape due to the cantilever and a distortion on the left side due to the tip sample interaction potential, okay? So this is the total number, okay? So here's what we're going to do. On the top left is interaction potential where we have plotted total energy of the system versus D, tip sample gap effectively, okay? And we're first going to look at free oscillations, then we're going to look at forced oscillations, okay? So here's what, the nice thing of doing a potential energy function is we just need to imagine a ball rolling in this landscape, right? And what we're going to do is ask the question, when we do the free oscillations, we're going to ask the question, how does the frequency of this ball, frequency of oscillation of this ball, depend on the oscillation amplitude of this ball, okay? And it's going to be a simple discussion, but it's relevant to the overall scope. So you can imagine that if you let's forget about this one. Let's go to the other one, okay? Okay, so let's say you place a ball in this potential well and just let it go, right? It's going to oscillate with some amplitude and some frequency, correct? So what I've plotted here on the top right is simply I'm recording what amplitude it oscillates with and what frequency it's going to oscillate with, okay? It's relevant. Then I move the ball up a little further and let it roll, right? Amplitude has become larger, correct? What happens to the frequency? So if I have a quadratic well and I take a ball and let it roll, it's got a frequency. If I let it roll with a different amplitude, what happens to the frequency? Anyone know the answer? Sorry? Decreases. Well, what if it's purely quadratic? Let's say if it's purely quadratic, what should happen? If the potential well is exactly quadratic, what is the relationship between frequency and amplitude of an oscillator? It should be constant because when you have a quadratic potential well, that means the force is a spring, is negative, is a gradient of the potential energy, right? And if it's a spring, you have a mass sitting on a spring, it doesn't matter what amplitude you're oscillating at, the frequency always remains the same, right? Exactly, square root k over m. So, what we expect initially is, as you change the initial location, what you expect is you're mostly in the quadratic part, and so as you change the amplitude, the frequency should not change. Okay? So it remains. So what I've done is, I've got an increasing amplitude. Amplitude is higher, but the frequency is still the same. Okay? However, once I start choosing to roll the ball at higher and higher, from higher and higher starting positions, right, you will see that it starts slightly, the frequency will start decreasing a little. Why is that? Because you're going to sort of approach that shallow part up there. Once the amplitude oscillations become large enough, where the ball is being released from a shallower part up there, but the curvature has become different, what will happen is, you know, you can imagine it's slower to roll off and then it gathers speed and, you know, it's fine, but it's slow out here, right? Because it's shallower. So the frequency goes down. So what you start seeing is, because of the tip-sample interaction potential, as you increase the amplitude of oscillation, the frequency starts changing. On the other hand, so the frequency starts decreasing as you increase the amplitude. However, if you go back up and start choosing the ball to start rolling from up there in the steep part, you get a flip, right? What's going to happen is you got a very sharp potential. So the ball is going to accelerate very fast and actually going to quicken during the entire process, right? Because it's now sitting on a much sharper slope, a slope that's much sharper than the quadratic would suggest. So it goes faster now. So you have an interesting situation where if you start releasing the ball from there, the amplitude becomes larger and the frequency starts increasing. And you have this interesting behavior. Okay? So very simple thing. You just got a cantilever separated from a surface. And if you just release this, ping it, and just study how the amplitude is connected to the frequency, this is what's going to happen. Hopefully the potential energy landscape gives you a physical intuition why it would happen, because it's easier to sort of visualize balls rolling on a landscape, right? This is very interesting. So you guys agree that what you have is the natural frequency of the oscillator depends on the amplitude. So as you increase amplitude, initially there's no change in frequency, but as the amplitude becomes larger, the frequency decreases due to the attractive forces. As the amplitude becomes larger, the frequency starts increasing due to repulsive forces. So you get this interesting backbone. So if your job is to make sure you're shaking the cantilever, you're tuning, if you're trying to make sure that you're always at resonance, what it means is, if you're trying to increase the oscillation amplitude of this cantilever, you first start driving the cantilever at its natural frequency, right? So the amplitude increases, keeps increasing, but if the amplitude increases a lot, the natural frequency is going to start shifting to the left due to this amplitude-dependent effect. So if you want to stay at resonance, you then need to reduce the frequency a little bit to keep it at large amplitude, and then keep building up so if your objective is to build the amplitude as much as possible, what you need to do is to be clever about it. You start shaking it, and it builds up in amplitude, but then the amplitude starts shifting, so you have to then go to slightly lower frequencies to keep it at resonance and build up amplitude more. But then as amplitude increases more, the natural frequency starts shifting to the right, in which case you have to then increase the frequency to the right to keep it at large amplitude. So as a result, the forced vibration response, which is when you shake it, behaves in the following way. So if you increase the frequency at small amplitudes, you get the linear response. As you start increasing the amplitude, you get this bending back. As you go to large amplitudes, you get this, which I showed before. Okay? So basically, think of it as the same thing as we have for the linear. In the linear case, all that happens is the natural frequency does not change, does not depend on the amplitude. So it always remains like this. Now you have a system where the natural frequency starts depending on the amplitude because of the interaction. So your resonance curve has to somehow keep tracking the natural frequency. The only way it can do that is if it bends to the left, bends to the right, and so on. Okay? So think of it that way. It's one way to look at this problem. Okay? So hopefully I've provided you a bit of a background on why this happens. Okay. So now let's talk a little bit about implications. So what implications does it have for amplitude distance curves? Okay. So this is something you're going to learn in the Thursday class. It's what's called an approach curve. So what's happening is you do the tuning far from a sample, you choose to be at resonance, and you have some amplitude, an initial amplitude. Okay. In this case, the initial amplitude is shown as A0 is 10 nanometer. So you've got a 10 nanometer initial amplitude. before you interact with the surface. You're at resonance, so the phase, initial phase is minus 90, basically. Or, in other words, the phase lag is plus 90. And then you have to simulate this as you approach a sample. Okay? So in this case, the parameters are, this interaction force is given by DMT interaction model, which you've studied already. All the other parameters are as shown. Let me show you what happens. And this is a Veda simulation. When you approach a sample, Z is the Z distance. So on the right, you're far from a sample. On the left, you're approaching the sample. Okay? The top curve is the amplitude of oscillation. So you have an initial amplitude of 10 nanometers. And as you approach the sample, you're approaching along the blue line. So at about Z equal to 10, the amplitude starts decreasing along the blue line, right? Keeps decreasing because of the interactions, right? So just as we expect. On the other hand, when you retract, move away from the sample, the amplitude follows the red line up until Z equal to 8 nanometers when it suddenly snaps out and jumps back to the same curve that was traced by the blue. This is what a Veda simulation will tell you if you just approach and move away. And the interesting thing is the Veda simulation also tells you what the mean interaction forces or the net interaction forces in the cycle are. It tells you that, so this is the y-axis in nanonewtons, 0 on the top, minus 6 nanonewtons at the bottom. You find out that when you approach, you're along the blue line and you have a negative net interaction force or a net mean force. But when you move away from this, when you withdraw from the sample along the red curve, the interaction forces are mostly net repulsive. Okay? Are positive. Positive forces are repulsive. Right? So this is what happens. And by the way, in air, when you do this experiment in AFM in air, this actually happens very, very often. Okay? And I'll show you results from this. Happens all the time. So this is interesting. So how is this connected to what I just showed you? So remember, what I showed you is you have this distorted resonance curve, which allows for the simultaneous coexistence of solutions that are net attractive or net repulsive interaction forces. That's what I showed you. What you see here is you're keeping the drive frequency fixed and you're approaching the sample. What you're seeing in this computer simulation is a switching between one of those kind of solutions and the other. All right? So in other words, when you're approaching the sample, the net interaction forces are always blue. So for whatever reason, you're sticking on the attractive branch of the solution. When you move away, you've switched for some reason to the net repulsive branch. Okay? Why is this so important? It's so important because if you look at the curve on the top right, I've circled 2 important points. Those are 2 points that have the same amplitude, correct? But they're at different Z's, right? And they correspond to different interaction forces. In one case, you're actually applying a net repulsive force, so you're really banging on the sample. In the other solution, you're in the net attractive regime, so you're just gently, mostly experiencing van der Waals forces, right? But both solutions have the same amplitude. And your controller is a little dumb, right? The controller simply knows or is asked to keep the amplitude constant. It's not intelligent enough to recognize that one is a net attractive, one is a repulsive state. So here's the big problem in tapping mode in air. The problem is that as you're scanning the sample, if during a scan, if you switch from one state to the other, and it can happen because the controller, all it sees is the amplitude. So you can imagine you're scanning in the attractive state happily, but for some reason you've hit an object and there are transients, the controller has some noise, there's some feedback noise in the system, there's different kinds of noises, and it gets tricked, and it switches to the other state, which happens to have the same amplitude. And after all it's asked to do is maintain a constant amplitude. So, it's going along happily maintaining a constant amplitude. It hits an object, it gets perturbed, it doesn't know where to go, and it says, oh, that's the amplitude I need to go to, goes back to that amplitude, and lo and behold, it's not the same state of oscillation as it was before, even though it's the same amplitude. it's moved from either a net repulsive to a net attractive, right? And if this happens during a scan, then you have very important artifacts that emerge out of it, okay? And this is what is one important thing you need to be aware of. And so this is why when you report an AFM image, it is extremely important to point out if it's in the net repulsive or net attractive regime or not, because the forces you're applying in the two oscillation states are completely different. In the net repulsive regime, you're applying a net indenting. You're actually connecting. You're actually touching the sample and pushing into it quite a lot, right? Whereas in the net attractive, you're mostly experiencing van der Waals forces, okay? So it's gentler if you're in the attractive regime. Now, why it's important is because the very height of any object you're measuring is going to depend on how much force you apply, doesn't it? Right? So if you're going to apply an attractive force, a net attractive force, what do you think is going to happen to the height of the object that you observe? So if you have a net attractive force, so you all know about the tides in the oceans, right? Why do they happen? It's the gravitational pull, isn't it? Right? That causes surface to rise up a little bit. So what will happen if there's a net attractive force between the tip and the sample is you expect actually the material to be pulled up gently a little, net, right? Whereas if you have net repulsive force, you expect it to be pushed down a little bit inside. So what you expect is when you're in the attractive regime, the height of an object that you image should be higher than the same object imaged in the repulsive regime, although the amplitude of oscillation in both those states is the same. But same object can be measured higher or lower depending on what state you're in. That's why it's extremely important when you report an image to point out, are you in the attractive or repulsive regime? How do you recognize it? So if you go to the article in the Reader, Garcia and Perez, they point out a scheme by which you can try to look at this. So here's again on the top left the amplitude versus distance curve, blue approach, red retraction. Below is shown the phase, okay? And the phase lag far from a sample when you're beyond 10 nanometers z distance, the phase lag is 90 degrees. When you're in the attractive region on the blue curve, the phase lag becomes above 90 degrees. When you're in the repulsive region, net repulsive state, the phase lag is less than 90 degrees. So that is your signature to identify whether you're in the attractive or repulsive regime. So the recommendation is when you do an approach curve to choose your set point amplitude, always plot the phase also with it, right? Always plot the phase. If the phase lag is greater than 90 degrees, you know you're in the attractive regime and your imaging state is set in the attractive regime. If, on the other hand, the phase is switched and is below 90 degrees, phase lag is below 90 degrees, then you're in the net repulsive regime of oscillation, okay? This is the key thing. And here are some experimental examples of why this is so important. I'm showing you a couple of examples again from Garcia and Perez's review article. So this was an experiment where these were indium quantum dot samples, and this is a hard sample. I'll show you another example of the soft sample. The top is an amplitude versus z curve, A versus z curve, right? In this case, as they were approaching the sample, they went down along the L branch, and this time the transition or the switching happened during the approach, okay? Whereas our switching, when we showed in the simulations, happened upon retraction. Here it happens upon approach. They found that suddenly there's a change in amplitude and it goes down. By the way, you might think that, why do I need to look at the phase? Because if there's going to be a switch in amplitude whenever I switch from one state to the other, why don't I use that as an indicator? It's not a very good indicator. You should always go by phase, because there's some examples where you cannot with your eye tell if there's a jump in amplitude as you approach a sample. You just have to follow the phase. That's the most sensitive indicator, okay? All right, so L would be what we would call this net attractive oscillation state. H would be what we would call the net repulsive force state. What they've done is they've taken images of the sample at different set points. Remember, when you scan in tapping mode, you choose an amplitude and you scan. If you were doing the experiment, what amplitude would you choose? Well, you have huge variety of amplitudes to choose, right? You can choose 18 nanometers, 12, 9, 6. Who's stopping you? No one's stopping you, right? You can choose anything. And then the controller is simply going to make sure the amplitude remains constant. However, out of the 3 dashed lines, one choice is not a wise one. The other 2 choices are wiser. Why is that? The not so wise choice is the one in the middle, because when you choose that set point amplitude, the simple amplitude distance curve tells you that there are 2 z's at which you have the same amplitude, one corresponding to a net attractive, one corresponding to a net repulsive state. So that's not a wise choice, because as you're scanning, if your controller can get confused, 2 states that have the same oscillate, 2 z distances with the same amplitude, right? You don't want that to happen. You want this amplitude versus z curve to be monotonic, right? Just one value for every, but you don't get that. So here are images taken at L, at the topmost set point of 16 nanometers. That's the image taken on the very top, right? Topography image, and you see that throughout the scan image, it stayed in the net attractive regime, okay? And you know that because you've done the phase diagram and you know that that amplitude corresponds to attractive regime. So the top third of this image is taken in this attractive state. And the state did not switch during operation. The very bottom third is an image, topography image taken with 10 nanometers or 9.5 nanometer oscillation amplitude, which is the net repulsive, and it has not switched during the imaging state. So you get a nice image. Do you see that there's a difference in image quality between the top third and the bottom third? Which do you think is sharper? Top third or bottom third? Bottom third is a little sharper. So here's the other thing, that if you want to see profiles very nicely and shapes very nicely, you often need to be in the net repulsive, because if you're in the net attractive stage, you don't know how close you are, the tip comes to the sample. So whereas you touch the sample, you more precisely know what the topography is in some sense. So typically, again, it depends, because if it's a soft sample, you might crush it and you won't see anything. But for hard samples, being in the repulsive regime probably gives you a slightly better estimate of, topography, okay? But when you choose an oscillation amplitude set point in the middle, see what happens. You see these streaks that happen? If you thought it was just normal topography, if you didn't realize that there are artifacts, you would take that image in the middle, and your conclusion would be that to the right of that dot, you have a black region. By the way, height, the color coding is according to height. So you would say that, oh, my sample has a black deep trench to the right of that dot, when in fact it's not there, because you change the oscillation amplitude, it disappears. So it has to be an artifact. So what is happening is, you've chosen an oscillation state where initially you are in the attractive regime, right? And then what happens is, as soon as you went over the bump, there was a perturbation and the controller got confused and it went into the repulsive state, which means it brought the Z down further, right? Pressing down further to get the same amplitude, right? So if the Z goes down further, it means, and remember, what you're rendering is the amount the Z had to go up and down to maintain the constant amplitude. You suddenly are creating this artifact of a darker, deeper region, when in fact all you've done is the Z is pushing down more, because the oscillation state is now in the repulsive regime. That's what happens. So just by looking at the topography image, if you start thinking of what is happening, don't think of it as an image. Think of it as up and down. What is the Z piezo doing up and down to make this happen? And it becomes perfectly clear what's going on, okay? So at some point, when you stare at these things enough and you understand cantilever dynamics enough, you look at this image, you don't look at these images as images. You literally see the Z moving up and down and the cantilever oscillating. I mean, at some point, you won't look at these as images. You'll start imagining what the probe is really doing. Okay? So you'll learn a little more about this in the next class, but how do you switch between these states? How do you make sure you have more of repulsive, more of attractive? Soft levers and smaller amplitudes tend to make the probe stay in the attractive regime most of the time, whereas larger amplitudes and or stiffer levers are more likely to get into the net repulsive regime. Okay? All right. Now, one more example, again taken from the reader. This is a soft sample. This is an antibody sitting on mica, and this antibody is interesting because its shape actually has a trilobed structure. All right, and again, they do an approach distance curve. There's a jump that happens. They choose three different. They choose on the top is an image taken with the net attractive regime of operation, right? Net attractive oscillation state, and the topography shows you the three lobes very nicely, right? B is the same taken with a lower set point, which corresponds to a switch where you're in the net repulsive regime of operation, and see what the topography looks like. Bashed it completely because it's net repulsive, so you're applying a net repulsive force on it, and the height is really reduced. It flattens pretty much this antibody. All right. And in C, what they did is, after flattening it by operating into the repulsive regime, they switch back to the attractive regime by changing the set point so it's in the attractive regime, and scan again, and look what happened. Which means that this particular sample, by switching to the repulsive regime, you were applying such a high force that you basically completely inelastically just smashed it so that it did not regain its original shape after you got back to it. Okay? So this is, again, very important thing. So let me ask you a question before we end this lecture today. Is you've learned of, when we talk of attractive, repulsive, we've learned of three different definitions of attractive, repulsive, right? One, when we did static force distance curve, right? Can you guys tell me, what did we call an attractive? When is the cantilever in attractive regime when we did static force distance curves? Well, whenever the forces were negative. When there was a negative force, it's an attractive force. That's the definition for static AFM, when you're in the attractive and repulsive range, okay? However, when you do dynamic AFM, it's not about whether the force is negative or positive. It now becomes whether or not the force gradient is negative or positive. It's a completely different story, okay? I want you to think about it. Because you could have the net force is negative, but the gradient could be positive or negative, right? So the linearized analysis, we talked about attractive gradients and repulsive gradients, which are not the same as attractive forces and repulsive forces. Okay, I hope you understand that. And in the so let me just reinforce that point a little bit. Go back to this slide, where you have, this is the top right, has shown a tip sample interaction potential. That point, green point, corresponds to a point, number one, where the force, the static force in the cantilever is attractive or repulsive. What's the static force? What's the force, value of force at that point? It's negative. Negative is attractive. But, and the gradient here is positive, and remember, positive gradient corresponds to an attractive gradient. Now, what if that green dot were located on the left of the minimum? So somewhere to the left of the minimum. It would still have a negative force, because the force would be negative. But the gradient would be repulsive. So if that green dot were to the left, right, but still so that the value is negative. So what I'm saying is, be aware of three different concepts. One, the mean force, the static force on a cantilever can be attractive or negative or repulsive. And the gradient that it encounters can be repulsive or attractive, but they're not the same things, right? You can have a negative static force, but you can have an attractive gradient, or you can have a negative attractive force and have a repulsive gradient. So be careful about this. And now, when we talked about tapping mode, we are again talking of an attractive and repulsive regime. what do those regimes have to do with attractive gradients and positive gradients and stuff, right? So there are many, the word attractive repulsive has been used fast and loose quite a lot so far. I want to quickly lay out that in each case, there was a different meaning of it. In the tapping mode, when we say switching from attractive to repulsive, our definition of attractive is simply that the net interaction force between the tip and the sample during an oscillation cycle is negative. That doesn't mean that it does not touch the surface, right? You could have a situation where as shown on the right here, your oscillation could go down and actually the tip sample interaction force could become a little positive also. But so long as the net interaction force is negative, we would call that an attractive regime oscillation as far as tapping mode is concerned. Okay? So, the word attractive repulsive in each case has a different meaning, and you have to be aware. Don't just think it's attractive force, so it's in the attractive regime, so it's not touching the sample. It's not true. It's just the net, in tapping mode, it's just the net interaction force is going to be negative. So as long as it's mostly an attractive force and a little repulsive force, that's also okay. Okay? So these are very subtle, important differences. Right? So with that, we end. And for the next lecture, please bring your laptops along. We're going to do Veda simulations of these approach curves, look at these jumps, and see how you can minimize them and so on. So we'll do that in the next class. Okay? Thank you very much.